Well, today we're going to do all the notes for Unit 3A, which is about quantitative properties of matter. We've been talking about counting atoms and how chemical reactions happen, but we haven't been very quantitative. We haven't worked with a lot of numbers yet, except for subscripts and coefficients. But now we're going to start looking at how to handle actual measurable quantities of matter. And then later on, we're going to start blending these two ideas together, quantitative properties with our knowledge of how chemicals behave. The first thing we want to do is talk about the difference between quantitative and qualitative measurements. Qualitative measurements are ones that use no numerical scale. They describe properties in general terms that don't use a numerical scale. Here are examples. If I said, that water is hot, that's qualitative. It tells you something about it without actually using a number. Or this box is heavy. That's also an example of a qualitative measurement. There's no numerical scale, but you get the idea of what I'm talking about. A quantitative measurement, which we often use in the sciences, uses a numerical scale to describe a property. Like instead of saying the water is hot, I could say this water is 95 degrees C. Or instead of saying that box is heavy, I could say that box weighs 80 pounds. We're going to focus in this unit on quantitative measurements. The properties that we measure with these quantitative measurements can be divided into two different categories. One is called extensive, and intensive is the other. Extensive properties depend on the size of the sample. How big of a sample do you have? If it's bigger, that extensive property will be larger. If it's smaller, then it'll be smaller. Intensive properties, on the other hand, are independent of the size of the sample. It doesn't matter how big it is, the property will be the same. Temperature would be an example of that. A really large fire could have a temperature of 1300 degrees Fahrenheit, let's say. A very small fire could also have that same temperature. Density would be another example of an intensive property. A small piece of lead and a large piece of lead are going to have completely different weights, but their densities would be the same. So there are some properties that don't change depending on the size. Those are intensive properties. Often, intensive properties are ratios of one quantity, one extensive property to another. And density is a good example. Density is a ratio of mass, which is similar to weight, and that's extensive. That's going to get bigger or smaller depending on how much you have, and volume. That will get bigger and smaller depending on how much you have. But the ratio of those two extensive properties is an intensive property. So let's look at some of the extensive properties that are used in chemistry. Here's one, very common. It's probably the thing we measure the most in chemistry is mass, because we're studying matter, and this is just a measure of the amount of material that's present in a sample. In English units, we commonly think about how much is there by using terms like ounce or pound or ton. Those are really not masses. They're weights. But we use weight and mass sort of interchangeably with an understanding that we're always talking about measuring them at the same place. Scientists most often use the SI, which is abbreviation of French words that mean international system. It's a system that we've agreed on throughout the world for measuring things. The standard unit in the SI system is the kilogram. A kilogram is roughly the mass of 2.2 pounds of weight. We're going to measure mass by using a balance. We have electronic balances in our classroom, and they read out, the way we've got them set, in grams. So this set of keys, just to give you a rough idea of what a gram is, this set of keys I put on there weighs 76.57 grams. A gram is roughly the mass of a raisin, 1 gram. That's 1,000th of a kilogram. The balance really doesn't measure mass. It measures weight. This set of keys, or whatever's on the pan of the balance, pushes down on a little sensor here, and it measures how much force gravity is exerting on that sensor. So it measures weight, but it converts it into mass. You can use weight to determine mass because they're proportional to each other as long as your weight and mass are measured at the same location. For example, if I take this balance to the moon, that mass is going to be different, even though the mass of the keys would really be the same because the weight would change. Another property that we could measure in chemistry from time to time is distance. Everybody pretty much knows what distance is. It's how far it is between 2 points. So if I have a point here, how far is it in between? The quantity that we use to measure that is called distance. We are familiar with the English units of inches and feet and miles, yards. Those are all ways of measuring distance in English. But in the SI system, the standard unit is a meter. A meter is a little bit bigger than our yard. Most people are fairly familiar with how much a meter is. In chemistry labs, a meter is pretty big for most of the things that we end up measuring. So when we measure length, we're going to use probably more often the centimeter. A centimeter is 1/100th of a meter. And you can see from this ruler that a sugar cube is roughly a centimeter across its edge. Another extensive property is time. It's pretty hard to come up with a good, simple definition of what time is, but we all have a sort of a feel for time being like elapsed events. The English and SI units are the same for time, and that's the second. We can measure this with a clock. People who have to measure things very, very precisely have to have other methods, and so there's a standard unit for the second that's defined based on something really precise. Another extensive property is a volume. Volume isn't actually something you can measure directly. It's made up of three measurements: length, width, and height, really. It's three lengths in three dimensions. The amount of space something takes up in English units is measured with cups, pints, quarts, gallons, barrels. There are pecks. There are lots of English units. In the SI International System, the standard unit is a cubic meter, which is a meter by a meter by a meter. A cubic meter is a really large volume. It's way too big for most practical purposes in chemistry labs. And so instead of using a cubic meter, we're going to use something much smaller than that. A liter would be an example. There are 1,000 liters in a cubic meter. And even smaller than that, we will often use milliliters. A milliliter, there are 1,000 of those in a liter. A liter is approximately equal to a quart in our system. Most people are familiar with liters because beverages are often sold by the liter, even in this country. If you think about a milliliter is actually equal to 1 cubic centimeter. So think about a sugar cube that's 1 centimeter by 1 centimeter, and then it's 1 centimeter thick as well. Well, that's a milliliter, or a cubic centimeter. Sugar cube is about that volume. 1,000 of those approximately would fit into a liter. We measure volume with various glassware in chemistry lab. If we don't have to be very precise, something like an Erlenmeyer flask, like this thing here, has got some measurements on there. That's not very precise. Same thing with beakers. There are measurements on there that can tell us roughly how much volume is in the beaker. If we need to be more precise, we have to use this tool. This is called a graduated cylinder, and the graduated cylinder can measure to the nearest milliliter or even more precisely. An intensive property that we measure in chemistry labs often is temperature. Temperature, there are scientific definitions, but a good working definition is how hot something is. The English unit for temperature, the one that we're familiar with from weather reports and just checking the temperature outside, is the Fahrenheit degree. In the Fahrenheit scale, the freezing point of water is 32 degrees Fahrenheit. And the boiling point of water is 212 degrees Fahrenheit. So the difference between those two significant physical events is 180 degrees. It's a 180 degree difference between the two. In chemistry labs, we will most often use the system of temperature measurement that the rest of the world uses, and that's degrees Celsius, degrees C. In degrees Celsius, the boiling point of water and freezing point of water are separated only by 100 degrees. Water freezes at 0 degrees Celsius, and it boils at 100 degrees Celsius. So this difference is 100 degrees. For reasons that have to do with using straight lines, and we'll investigate this more thoroughly when we study gases later on in the year, the SI standard unit is not the degree Celsius. It's something related to Celsius, but it's called the Kelvin. It turns out that with both the Fahrenheit and Celsius scales, you can go below 0 because things can get colder than the freezing point of water. It would be really nice for mathematical purposes to have a temperature scale that starts at 0 and has no negative numbers. So scientists have figured out the lowest conceivable temperature that there could ever be, and in the Kelvin scale, that's 0. So there are no negative Kelvin temperatures. It turns out that the lowest possible temperature there is, 0 Kelvin, is equal to negative 273.15 degrees Celsius. So that means if we wanted to convert, if we had 273, roughly, we're going to round this to 273 kelvins, that's about 0 Celsius. Add 100, 373 kelvins is about 100 degrees Celsius. So add 273 and you will get the Kelvin temperature from any Celsius temperature. So temperature is an intensive property because it doesn't matter how big or small the object is, temperature will be the same. Another important intensive property in chemistry is density. We talked about it briefly before. Density is the ratio of the mass of a substance to its volume. So by definition, mathematically, density is the mass of an object divided by the volume of the object. Well, mass in the English system might be measured in pounds. Volume in the English system might be measured in cubic feet or something else. So there are all kinds of different density units. The SI standard unit for density is the kilogram per cubic meter. A kilogram turns out to be pretty large for what we measure most of the time, and a cubic meter turns out to be really large for what we measure most of the time. So in chemistry, we're more often going to use grams per milliliter, which would be the same as grams per cubic centimeter. One thing that's very handy to know is that for water, 1 gram is pretty much equal to 1 cubic centimeter. They're not equal, but the mass of 1 cubic centimeter is about a gram. Sometimes for gases, we might use grams per liter because they don't have very much density, and you need a bigger quantity to get a significant mass. Density gives us a good opportunity to see how scientists use algebra and use equations as problem-solving tools, as well as definitions. Here's a good example. What is the density, this question is asking, of a sample of a liquid that has a mass of 13.645 grams and a volume of 10.01 milliliters? Well, density, by definition, is mass divided by volume. So to find the density, I'll plug in the mass, 13.645 grams, and I'll plug in the volume, 10.01 milliliters, and I'll figure out what my answer is. Well, grams and milliliters don't cancel out or anything, so the unit is just grams over milliliters, grams per milliliter. When you see divide by in math, in English you should think per. Per means divide by. Now let's do the calculation. 13.645 divided by 10.01. Here's what I get, 1.363. We'll have some formal rules for this later on, but a good rule to go by is you should never use more digits in your answer than you actually have in the problem. So 4 digits there, I'm going to go 1.363 when I report my answer. So there's the density. Now we're being asked what is the mass of a 3 milliliter sample of a substance whose density is 13.55 grams per milliliter. Starting from the same point, starting from the definition of density, density is mass divided by volume. Now what I want to isolate here is not density but mass. I can do that by multiplying both sides by volume. If I do that, volume cancels out and I get this equation. Mass on the right equals density times volume, which is what I ended up on the left. So I'll just plug my numbers in. To find the mass of this sample, I take its density, 13.55 grams per milliliter. Remember, grams per milliliter means grams divided by milliliters, times, I'm going to use a vertical line for times here, 3 milliliters, 3.00 milliliters. Well, what I see happening with units now is milliliters are on the top and the bottom. Milliliters divided by milliliters is just 1, so that goes away, it cancels out, and I'm going to end up with units of grams. Now I'll do my arithmetic. 13.55 times 3. Again, I shouldn't use more than 3 digits here because I had 3.00 in my volume, so I'll round this off to 40.7 grams. Here's another problem. This is asking what is the volume of something, and we know its mass and we know its density. Well, from the definition of density, density is mass divided by volume. This time it's volume that I want to isolate. I'll start out by multiplying both sides by volume to get it out of the right-hand side. That leaves me with this equation. Volume times density is equal to mass. But I want to isolate volume, so now I'm going to divide both sides by density. When that happens, density cancels, and I end up with this equation. Volume is equal to mass divided by density. Well, volume, then, is equal to 12.65 grams for our sample, divided by 7.874 grams per milliliter. Here's the units. Grams cancel out. I have it on the top and the bottom. So I end up with 1 over the reciprocal of milliliters. Well, that's just milliliters. Now I'll do my arithmetic. 12.65 divided by 7.874 grams per milliliter. I'm going to round this up to 4 digits, so 1.607 milliliters is my answer.